And now we go to the last chapter, to the last section of this nice, very nice part, in my opinion, of the complex numbers, which is powers and roots of complex numbers. So, and so here it is clear that if we start from a number z, which is rho e to the I theta, so I use the exponential notation because it is the most comfortable, it is the fastest to use, to be used here. It is clear that z squared, here I have to take the product of the moduli, so rho times rho is rho squared, and then the sum of the arguments, so e to the 2I theta, z cube is equal to rho cube e to the power 3I theta, and so on and so on. Okay, so z to the power n is equal to rho to the power n e to the I n theta. Okay, and of course this is well known as the Moivre formula, and of course then one has to add or subtract two k pi to n theta in such a way that n theta plus 2k pi lies in 0 to pi, or the interval of the argument that we want to use. Okay, it doesn't change anything, but just that the argument by definition must belong to some predefined interval whose size is exactly 2 pi. But let me give you an example of all of this. So, example, one has to compute z cube with z is equal to minus 1 plus I square root of 3. Okay, so first you have to understand what is the modulus, and the modulus is very simple. Z is square root of 1 to the square plus square root of 3 to the square, so it is 1 plus 3, which is 4, so the modulus is exactly 2. And now the argument is to be understood with some attention, and here z is minus 1 in the x-axis and plus I square root of 3, so it is something like here, and so this is minus 1, and here so you see here that this is pi over 3, and this is pi over 6. Okay, so theta will be pi over 2 plus pi over 6, which is Here you put here 6, here 3 pi plus pi, so it's 4 over 6, so 2 over 3 pi. So z is equal to 2 e to I 2 over 3 pi. So z cube is equal to 8 e to the power e 2 pi, but 2 pi is equivalent to 0, so z cube is equal to 8. Okay? And so from this is for what concerns powers, and now we go to roots. So as a definition, given z complex number, there are so any complex number w such that w to the n is equal to z is called n root of z. So, and now we can give a result in the form of a theorem. That says that every complex number z, which is not vanishing, has exactly n distinct n root. Okay, and moreover, if z is rho e to the I theta, then these n roots are given by z, the kth n root is zk, is the n real root of rho, and then e to the I rho theta over n plus 2 pi over n k, with k equal to 0, 1, n minus 1. Okay, and I want to show you by a picture what is how this this construction is made. Here you have it doesn't work. Let me try again. Okay, it has stopped working, so I will try to be a bit more precise. So, a long time ago, when I tried to close this circle, it gave me the perfect circle, so it has stopped. And this is the artificial intelligence. Everything changes in the worst possible way. So, here you have z, for instance. This is z, and this is theta. And then you want to find, for instance, the cubic square root with n equal to 3. Then you have first, you divide theta by 3, and this is z1, and this is theta by 3, and modulus of z1 is the cubic root of the modulus of zeta, and then you add, notice here, 2 pi over 3, and so this is, sorry, zeta 0, not zeta 1. This is zeta 0, according to our notation. And then you basically divide the circle in 3 equivalent sector of amplitude 2 pi over 3, and this is zeta 1, which is modulus of zeta, and then you take the cubic root, and then e to the I theta over 3 plus 2/3 pi, and here this is zeta 2, which is endowed with the same modulus, e to the I theta over 3 plus 4/3 pi. Okay, this is the formula. So geometrically, when you have to take the roots, you basically have to draw a polynomial, a polygon, in this case a triangle, with a number of sides which is exactly the same as the degree of the root you are looking at, and the intersection of these angles of the polygon with the circle whose size is exactly the nth root of the modulus of the number you are given, these intersections give you the roots. Okay, then at the beginning this is quite difficult to understand, but then when you do some exercise it becomes very easy, and I give you the proof of this theorem. The theorem is very easy, and so start with z equal to rho e to the I e theta, and then w delta e to the I e phi. Then you have, by the Moivre formula, you have that w to the n is equal to delta to the n e to the I n phi. Okay, so now you have to impose that a system, and the system tells you, of course, that the two moduli of w to the n is equal to the modulus of z, and the argument of w to the n is equal to the argument of z, but there can be some 2k pi with k in z. Okay, when, of course, this has to be contained in the interval 0 to pi, and so then the first equation tells you that delta to the n is equal to rho, so delta is equal to rho to the power 1 over n, and the argument tells the following, that n phi is equal to theta plus 2k pi, so phi must be equal to theta to the n plus 2k over n pi, and of course k varies in zeta, but when you saturate up to the n minus 1 step, and then you go to the n's, you just repeat it. Okay, if k is equal to n, then here you have 2 pi, so you are repeating the same things. So by periodicity, so this k, this computation of the k's must stop by the periodicity of functions. Sine and cos. Okay, so this is the end, and I give you an example in order to be more specific, and the example is the following. So compute the fourth roots of -1. Okay, so -1 is what? Is cosine of pi plus I sine of pi. So it is 1 e to the I pi. Okay? Now, we are applying the theorem on the roots of a complex number and then we have that z0 is the fourth root of 1 and then e to the I p over 4. Okay? And so this means that is I and then cosine pi over 4 plus I sine pi over 4, and this is 1 over square root of 2 plus I over square root of 2. Z1 is again fourth root of 1, which is again 1. And then you have e to the I pi over 4 plus 2 pi over 4, which is pi over 2. So this is cosine 3 over 4 pi plus I sine p over 4, 3. And now the cosine is negative, so it is minus 1 over square root of 2 plus I over square root of 2. And then Z2, now you go again and again, and here you have cosine 5 over 4 pi plus I sine 5 over 4 pi, and this is given by the two negative components. And then the last is zeta 3, which is cosine of 7 over 4 pi plus I sine of 7 over 4 pi, and this is 1 over square root of 2 minus I over square root of 2. And so if you want to represent in some way, oh, it is back. What a good news. Okay. If you want to represent it, here we have minus 1 is here. And then we have this 4 vectors. Sorry, not. Let me use the blue. 4 vectors here, 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 and here. So this is Z0, Z1, Z2, and Z3. Okay. And so this is the end. I won't just tell you what is, from cultural point of view, what says the fundamental theorem of algebra says, given a real polynomial, P of Z, which is A naught Z to the M plus A1, sorry, Z to the power M minus 1 plus dots up to AN equal to 0 with all AJ complex. This can be always factorized as A naught, Z minus Z naught to the power M naught, Z minus Z1 to the power M1 up to Z minus Z naught to the power Mk, where Zj is the jth root and Mj is its multiplicity. Okay? So we can say that every polynomial has of degree n has exactly n complex roots, and every root must be counted with its multiplicity. And for instance, as an example, consider P of Z is equal to Z fourth plus Z square. This is Z square plus 1, and here you have to stop, but now you can write Z square, Z plus I, Z minus I. So 0 with multiplicity 2 is a root. I with multiplicity 1 minus I with multiplicity 1. So it is not the case that here we have I and here minus I, because a corollary of the fundamental theorem of the algebra says that if you have P of Z, again like here, but this time the coefficients are real, so if Z, oh sorry, let me call it W. If W is a root of P with non-trivial imaginary part, so imaginary part of W different from 0, then the complex conjugate of W is a root of P. 2. Okay, this is a very nice theorem, and indeed let me say why. Indeed, P of zeta bar is equal to A naught zeta bar to the n plus A zeta bar to the power m minus 1 plus an is equal to 0. This is why, because zeta to the k complex conjugate, oh sorry, this is for the next passage, and of course, because this is rho to the k e to the minus I k theta, and this is equal to rho to the k e to the I theta minus a theta to the power k. Okay, this is a very easy computation if you use the exponential notation, and then you go forward And then, sorry, you can P of zeta bar, this is equal to that, and then you can also write A0 like A0 bar because it's real, so it is equal to its conjugate, zeta to the n bar plus A1 bar, zeta n minus 1 bar plus an bar. So this is P of zeta bar. But P of zeta is 0 because zeta is a root, so it is 0 bar and this is 0. So if you have a real polynomial, the coefficient must be real. If you have a real polynomial, then complex roots appear together with their conjugate. Okay, we will use this corollary. When studying the second order differential equations, that are linear and with constant coefficients. So you're asked to remember very well this result. Okay? And the last thing I want to tell you, I forgot to tell you, another remark which is very important. C is not ordered in the sense that it admits no ordering that is compatible with the ordering of the reals. Suppose by contradiction that C is ordered compatibly with reals, then either I is positive or I is negative. So if I is positive, then when multiplied by I, this is conserved. I squared larger than 0. But I squared, it is minus 1, which is less than 0. So it is not compatible. So this ordering is not compatible with the ordering of the reals. That of the reals. If, on the other side, I is less than 0, then complete as a homework. And the last homework on complex number is the following. Prove that sum and product of complex numbers are commutative, associative, and distributive, one with respect to the other. So, and this is the end of complex numbers. Now we are left only with differential equation. Thank you very much.